Hello learners! Have you ever looked at a butterfly and noticed how its wings are mirror images of each other? Or thought about how spinning objects in physics always rotate around axes with specific symmetry? In mathematics too, some matrices exhibit symmetry, and these special matrices are more than just beautiful, they simplify real-world problems in physics, engineering, statistics, and more. A matrix that behaves predictably when transposed, either by remaining unchanged or becoming its own negative, is extremely useful in computation. For instance, symmetric matrices are vital in optimization, quadratic forms, and principal component analysis. Whereas skew-symmetric matrices appear in vector algebra, cross-product operations, and rotational systems in physics. Today, we'll learn how to identify, use, and even decompose matrices into these special types, helping us unlock powerful simplifications in linear algebra. Let's begin with symmetric matrices. A matrix A is symmetric if its transpose equals itself. Mathematically, that's A transpose equals A. This means for every element, A sub ij equals A sub ji, indicating mirror symmetry across the diagonal. But here's the key point, only square matrices can be symmetric. Because the transpose changes the shape from m by n to n by m, so both must be equal for symmetry to hold. Let's look at an example. Matrix A, first row 3, 2, 3. Second row 2, 1.5, 1. Third row 3, 1, 1. Now transpose it and you'll see it's exactly the same. Such symmetry isn't just visual, it allows for easier computation, especially in solving systems of equations or optimizing real-world models. Now, let's move to skew-symmetric matrices where things flip quite literally. A matrix A is skew-symmetric if its transpose equals negative A, that is, A transpose equals negative A. This means for each element, A sub ji equals negative A sub ij. So, if element at row 2, column 1 is 5, then the element at row 1, column 2 must be negative 5. But there's something special here. If A sub ii equals negative A sub ii, then 2 times A sub ii equals 0, which implies A sub ii equals 0. All diagonal elements of a skew-symmetric matrix must be 0. Here's an example matrix B, first row 0, E, F, second row, negative E, 0, G, third row, negative F, negative G, 0. This structure appears in rotation matrices, physics, and antisymmetric systems where directional forces or movements cancel each other out. Now here's an elegant identity. If you take any square matrix A and add it to its transpose, that is A plus A transpose, the result is always symmetric. Why? Let's prove it. Transpose of A plus A transpose equals A transpose plus A, which is the same as A plus A transpose again. So, the transpose of the sum equals the sum, that makes it symmetric. Similarly, if you take the difference A minus A transpose, it always gives a skew-symmetric matrix. Again, the transpose of A minus A transpose equals A transpose minus A, which is negative of A minus A transpose. That satisfies the skew-symmetric condition. So, any square matrix can be split into 2 parts, one symmetric and one skew-symmetric. Let's now write this concept into a formal expression. Any square matrix A can be written as A equals 1/2 into bracket A plus A transpose bracket plus 1/2 into bracket A minus A transpose bracket. The first part, 1/2 of A plus A transpose, is always symmetric. The second part, 1 half of A minus A transpose is always skew symmetric. This process is called matrix decomposition, and it's highly useful in signal processing, quantum mechanics, and matrix simplification techniques. Let's work through a quick example. Take matrix B, first row 2, 2, 4. Second row, -1, 3, 4. Third row, -1, -2, 3. Step 1. Find B transpose. Step 2. Compute P, which equals 1 half into bracket B plus B transpose. That gives us the symmetric matrix. Step 3. Compute Q, which equals 1 half into bracket B minus B transpose. That gives us the skew symmetric matrix. Now verify P plus Q equals B. This shows that any square matrix, no matter how messy, can be cleanly broken into a symmetric and a skew symmetric part. It's like separating the calm from the chaos and using each part where it's most useful. Let's wrap it all up. A matrix is symmetric if its transpose equals itself, A transpose equals A. It is skew symmetric if its transpose equals its negative, A transpose equals negative A. Skew symmetric matrices always have zeros on the diagonal. Only square matrices can be symmetric or skew symmetric. Any square matrix A can be expressed as 1 half of A plus A transpose plus 1 half of A minus A transpose. This decomposition helps simplify matrix operations, validate algebraic identities, and support advanced topics like eigen decomposition and Fourier transforms. And that's the beauty of understanding symmetry in matrices, a small insight that brings great computational power. See you in the next session where we apply these concepts further. Happy learning!